this idea of an initial value problem where you have some function and some point, and you want to know an antiderivative of that function that goes through that point, it might seem like kind of a niche thing at first, but in fact it's an extremely common type of problem to run into. Let's look at one example of that. So suppose we have a rock that we throw upwards at a speed of 15 meters per second from the top of a 50-meter building. Let's find the height of this rock as a function of time, and let's find when the rock hits the ground. Right? If we can find this function h of t, then we can just set it equal to 0 to find the time when it hits the ground. Keep in mind that near the surface of the Earth, gravity accelerates objects downwards at 9.8 meters per second squared. And while we're at it, let's assume the air resistance is negligible. That's a pretty safe assumption as long as your rock is a decently dense rock. If you were going to throw a piece of paper, we couldn't neglect air resistance. But for rocks, it's probably not too big of an approximation to just ignore air resistance altogether. All right, so what we need to do is somehow relate the function that we want, h of t, to what we know about how the rock moves. And we know two things. First of all, the acceleration of the rock is 9.8 meters per second squared, and that's downwards. And this is constant, right? The only force acting on this rock, since we're ignoring air resistance, after we throw it, the only force acting on this rock is gravity, so this acceleration is going to be constant. We also know that the starting velocity of this rock is 15 meters per squared, 15 meters per second. Now this velocity, this isn't a constant velocity. This is the velocity of the rock only at time 0, right? That's the velocity at the instant we throw the rock. So as soon as time progresses past the instant we throw the rock, this velocity is going to start changing because gravity is going to be slowing it down. So this acceleration, that's for all values of t, but this velocity is not for all values of t. Okay, I guess one other thing we know about how the rock is moving is we know it starts 50 meters in the air because that's where we are when we throw it. All right, so we know something about acceleration, and we want to find, or we know an acceleration function, right? Since the acceleration is 9.8 meters per second squared for all times, at least after we throw the rock, then that means that our acceleration function is 9.8. But it's downwards, so we should put a minus sign in front of this. And this is for time greater than or equal to 0, right, after we throw the rock. What we want to know is the height function. So how is an acceleration function related to a position function? Well, acceleration is the second derivative of position, right? So the derivative of our height function is the velocity function, and the derivative of the velocity function is the acceleration function. So, right, we've run into situations where we know a height function and we take two derivatives to find an acceleration function, but this is going the other way. This time we know the acceleration function and we want to work our way backwards to the height function. Well, if derivatives would take us forward, it's going to be antiderivatives that take us backwards. So I guess to find the velocity function, right, first, since we know acceleration, first we'll have to find velocity and then we can find the height function. So we know that the velocity function, since acceleration is the derivative of velocity, velocity is the antiderivative of acceleration. And we know the acceleration function. It's negative 9.8 meters per second squared. I'm going to neglect units just because the units all work out. So what is the antiderivative of negative 9.8? Well, it's negative 9.8 t plus a constant, right? Don't forget about the constant. Can't forget about the constant. Well, anytime you are calculating an antiderivative, you're going to have this constant. You should always ask yourself, do I have enough information to figure out what this constant is? And enough information always means some data point for this function. So do we have any point in time where we know the velocity? And the answer is yes. We know the velocity at time equals 0. So we can use this data point to figure out what this c constant should be. So we know that the velocity when time is 0 is 15 meters per second. And this is positive because we're throwing it upwards. And if we plug t equals 0 into our velocity formula here, we get 0 plus c. And that means that this constant is actually just 15. So now we know our full-blown velocity function. It's negative 9.8t plus 15. All right. Well, now that we've found the velocity function, we can get the height function just by working backwards, by doing another antiderivative. So we know that our height function is the antiderivative of our velocity function. And we know our velocity function. It's negative 9.8 t plus 15. Okay, so now we can find this antiderivative. It's negative 9.8 times the antiderivative of t is 1/2 t squared plus, and then antiderivative of 15 is 15t, and then of course plus a constant. Now I'm calling it c again, but it's not the same c as before, so this is a different constant. If it makes you uncomfortable to reuse this name c, you could use some other name. So maybe capital D. I don't know, D is dangerous in calculus class. Maybe let's use capital E instead. So we have some arbitrary constant, well, some constant that shows up here, and we don't know what it is yet. We'll have to think about it if we can figure it out. So here's a formula for our height function. We could simplify it a little bit. 9.8 over 2, that's 4.9. So negative 4.9 t squared plus 15t plus some constant that we don't know yet. So now we have to ask ourselves, do we have enough information to figure out e? What would enough information be? Well, the information we need to figure out this constant is a data point for this function. We need to know at least one point on the graph of this height function. Do we know anything about the height of the rock? Yes, we do. Since we're starting at 50 meters, that means h of 0 has to be 50. So we can use that as an initial value for this height function. So h of 0 has to be 50. Now we can plug t equals 0 into our formula for h, and we get, let's see, 0 plus e, and so e has to be 50. So now we know our height function. That's negative 4.9 t squared plus 15t plus 50. If you've taken a physics class, this sort of thing might look very familiar, but now you see where all of these pieces come from. This minus 4.9, that's really half of the acceleration due to gravity, and that half came from this antiderivative. And this 15, well, that's just the initial velocity, but with one antiderivative, which creates the t that's sitting here. All right, so here's our height function. Remember, that was the first thing that we wanted to find, the height function. The second thing we wanted to find was when the rock hit the ground. Well, the ground is height 0, so to find when the rock hits the ground, we can just set this thing equal to 0. So 0 equals minus 4.9 t squared plus 15t plus 50, and then solve this equation. Well, this equation is quadratic, and the coefficients are messy, so let's just throw it into the quadratic formula. So t is minus 15 plus or minus the square root of 15 squared minus 4 times negative 4.9 times 50 all over 2 times negative 4.9. Okay, so let's see. Let's simplify our signs a little bit. We can make both of these plus. That also switches this plus minus to minus plus, but it's still plus or minus. Doesn't matter which order you write them in. So let's dump this all into a calculator. One thing to notice is that this stuff inside the square root is actually going to be bigger than, well, once you take the square root, this second term here is going to be bigger than 15. So one of the solutions we're going to get is 15 minus something bigger than 15. That's going to be negative, but this height function doesn't work for negative t values. Remember at the very beginning we said that the domain for our function was positive, the domain for our acceleration function was positive t values. So we can't have negative t values. So we're going to discard the negative possibility. We know ahead of time that that isn't what we're looking for. So with that said, let's dump everything into a calculator. So 15, we know it's going to be plus square root of 15 squared minus 4 times negative 4.9 times 50, close my square root, and then divide by 2 times 4.9, which is 9.8, and I get 5.0728 approximately, and that's a time, so that's going to be in seconds. So the rock is going to hit the ground after a little more than 5 seconds. You can see that from this pretty sparse information, just knowing that gravity, the constant acceleration due to gravity, an initial velocity, and an initial position, we were able to come up with a position function that we could use to answer all sorts of questions about this rock. When it reaches the top, how high at the top of its arc is, anything like that. We could figure out once we've used antiderivatives to find this height function.